Okay, so we have integration by parts now, which is a new technique for tackling integrals that might be too difficult to do any other way. It's based on a kind of magical looking formula we give you, which says that the integral of u dv equals uv minus integral v du. Now this is a modified version of the product rule, actually, and if you're curious about that, your instructor can show you where that came from, but we're just going to accept it for now and see how we can use it. What it says is, if you have an integral, you can replace it with some stuff and a different integral. So it's saying, if this integral is too hard, maybe this other integral here will be more to your liking. You might find this one easier. And the relationships in here are, they're using u and dv here to show that these pieces look unrelated. Neither one of these is the integral of the other, or the derivative of the other. And the integral that you switch to ends up having, instead of this piece, we have its derivative, and instead of this piece, the dv, we have its antiderivative. So integration by parts says, if you've got two pieces and you can't figure out how to integrate them, you can differentiate one, anti-differentiate the other, and if you like this integral better, then go ahead. This uv minus integral v du is an alternate form that you can use. So let's see if we can apply that to our x cosine x integral we have here. I'm just going to write this out bigger. We have x, we have cosine x dx. Now, the way most people lay these out, and I do encourage this, is we're going to have to find u, du, v, and dv. We need values for all of these things because they're all part of the integration by parts formula. So one of these pieces, or some of these pieces, have to be our u, and the rest of them have to be our dv. This part, the dx, is derivative. It has to be included in the dv. So the question is, how do we allocate these things so that some of this is u and some of this is dv, as per our original integral? I'm tempted to show you the wrong way to pick this. Yeah, I'm going to switch to red, and I'm going to pick a bad integration by parts setup first, just to show you what happens if you do this incorrectly. I'm going to say that x dx here is our dv. This is red because it's wrong. I'm going to say dv is x dx. That means by elimination, this cosine x must be our u. Okay, so now we have to figure out what the other pieces are that go with this. If our original u is cosine x, its derivative would be negative sine x dx. That's not too bad so far. If dv is this, then its antiderivative would be 1/2 x squared, and no dx because we just did an antiderivative. So let's see what that gives us if we do integration by parts. This was our u dv, and the formula says that's integral to, or equal to, uv, which would be cosine x 1/2 x squared minus, and here's our new integral. It has v, which is 1/2 x squared, and du, which is minus sine x dx. So the minus will go out front. I'll use it to cancel this. And now we have sine x dx. And the question is, did this help? Now, I've been writing all this in red and saying it's wrong, so you probably know this didn't help. Here's the problem. Our original integral had x times a trig function, and we didn't know how to integrate that, so we did this tweak. And now we have x to the 2 times a trig function. If anything, this is worse. This is a more complicated integral because the power of x has gone up. We've still got a combination of a polynomial and a trig function, so this hasn't gotten us anywhere good. This is this can happen sometimes if you set up integration by parts, and you have to ask yourself when you get this new integral, did this make things any better? And in this case, the fact that it didn't means, okay, maybe I picked the wrong values for u and v. So I'm going to clear this out, and we'll show you, okay, what would be a helpful way to do this. Let's try a different assignment of u and dv. Last time, I picked the x and dx part as our dv. This time, I'll switch to a different color because we're going to do it right this time. I'm going to take these two pieces and say that those are dv, and I'm going to pick this x and let that be our u. So we'll just copy that over here. Our u is x, our dv is cosine x. Oops, sorry. Running off the edge of my frame. Cosine x dx. There we go. Okay, so now du is just dx. The antiderivative of cosine x dx is sine x. So now let's see what this formula gives us. It says this integral is equivalent to uv, which would be x sine x, minus integral v du. Now, is this better? This is much better because before we had a polynomial function times a trig function. Now we just have the integral of a trig function. We can do that. This is just x sine x. The integral of negative sine, if you think of this as negative sine x, then its integral is just cosine x. Or if you do this in fewer steps, we have this negative out here, and then the integral of sine x is negative cosine x, and then the negatives cancel and you get to here. And because this is an indefinite integral, don't forget your c, and now we win. So the takeaway from this is whatever you call u, you're going to end up differentiating. So it's a really good idea if your u is some power of x, because the derivative will take that down by one step. If this were an x squared, it would take it down to x to the 1. If this is an x, it takes it down to just dx, which is a big improvement. So you want u to be something that gets kind of worn down by having its derivative taken. You don't want your u to be something like a trig function because they have an infinite number of derivatives. If this is sine x, the derivative will be cosine x. That doesn't improve your situation. You had a trig function, now you still have a trig function. You want to take advantage of the fact that the u part gets differentiated. So generally you want this to be something polynomial. The v part is going to be anti-differentiated. You're going to take its antiderivative. So this is generally where you want something like a trig function where you do its antiderivative and it doesn't really change. If it was cosine, it'll become a sine. If it was a sine, it'll become a cosine. So the idea is the v part doesn't get any worse, and the u part gets better when you differentiate it. That's the situation you're trying to create when you pick your assignments here. So generally, try to make your u equal some power of x if you can. Then when you differentiate it, the differentiated version will be an easier integral, hopefully.